Hello students. In this video we're going to go over the second part of chapter 9. We're going to talk about linear regression. In this section it's multiple linear regression. Multiple means that there are more than two independent variables. The independent variables being x. So we are measuring multiple independent variables to see if there's any type of association, correlation, significance to the dependent variable y. So remember, once again, the independent variables are the ones that are used to make the prediction, and y is the one that we are trying to predict. So this follows the same process as the first part of this chapter in terms of what we will be doing. We're looking at measuring the correlation between the correlation coefficient between the independent variables and the dependent variable. As well, we will be developing a multiple linear regression equation and looking at the R-squared value. The R-squared value is a coefficient of determination from the first part of this chapter, but when we have more than one independent variables, the R-squared value is sometimes referred to as the coefficient of multiple determination. Ultimately, we will be looking at get rid of that. We'll be looking at developing and analyzing the hypothesis test approach. So once again, Pearson correlation coefficient R ranges from -1, showing a perfectly negative correlation, to +1, showing that perfect positive correlation. The regression line, using the same symbols or values. So y with that symbol above it is the estimated value of y is the intercept b0 plus the slope for variable 1 times the coefficient value times the value for x plus the slope for variable 2 times x2 plus the slope for variable 3 times that value for x, and so forth. R-squared value, coefficient of multiple determination. So we're going to look at analyzing, calculating some of those things as we go through an example. So the example that we will look at is this one. So it says that a realtor has collected the following data, on 7 homes, showing the cost to heat a home, average outside temperature, attic insulation, and the age of furnace, in an attempt to develop a model at which they could predict a home's heating cost. Is it a function of the outside temperature, attic insulation, age of furnace? Which of those variables, and there's probably other variables that they could include, but is this use of the 3 independent variables a sufficient model that we could actually use to predict heating costs? So we look at the data. I'm going to go into Excel here, and I'm going to run this data. So once again, we go into the Data tab, Data Analysis, Regression, input the Y. The y is our heating cost, including the label, and the independent variables x. We highlight all 3 of those. We make sure we have labels marked. We're going to go to a new worksheet, and there is our data, which I believe I already have. Sorry, thought I already had it somewhere. We'll keep it there. Let's just make more room for everything. Let's enter all those numbers. And let's reduce them to get rid of some excess numbers here that typically we don't need that level. And this. There we go. So a few things to point out. Here is Pearson correlation, that's R, and here is the coefficient of multiple determination, R-squared. So basically this accounts for, we can change that to a percentage if we want, accounts for 97.7%. So using the mixture of the independent variables, it accounts for 97.7% of the unknownness or variability of the dependent variable y. Here is the slope. Let's color some of this stuff in yellow here. We have 7 observations. These are the slope for the 3 independent variables, and this value here let's put that as another color, is the y-intercept. So we could go estimated cost of heating a home, y estimated, would equal the intercept plus, in this case, minus 18.7437 times the temperature, let's just abbreviate that as temperature, times x1 in this case, minus, the slope is negative 3.9886, let's call this attic, and then plus 13.9964 for the age. So if we knew the age of a furnace and how much insulation they had and the average outside temperature in a home, we could, using this regression equation, predict the estimated heating cost for that home. The one thing about the slope, look at the slope. This slope tells us that if we increase the outside temperature by 1 degree, the average heating cost of the home is going to fall by $18. So as we increase this y, because it's a negative slope, one increases, the other one decreases. This shows a positive correlation or positive slope. So these coefficient values are how much y will change by increasing the x values by 1 unit. So if the age of a furnace goes up from 7 years to 8 years, the estimated cost, the additional estimated cost to heat this home is $13.9964, or approximately $14. Okay, so we have found R value, R squared value, and we have developed an estimated regression equation. Before we can use this estimated regression equation, we need to determine if the model overall is significant, and we do that by looking at these values here. This is the test statistic for F. Let's just put that value in there, and this is the p-value for F for that test. And so our decision rule will always be, decision rule will always be to reject the null hypotheses if the test statistic is greater than the critical value. This is easier, quicker. Or, once again, we can make that same decision by using the p-value approach. Reject the null hypotheses if the p-value is less than alpha. Alpha is not specified in this question, so I'm just going to put up here that alpha, the level of significance, is going to be 5%. Seems to be a good value to have. So, use for the decision rule, to use the decision rule using the test statistic and the critical value. We know the test statistic, it's 42.4547. We don't know the critical value. The critical value for multiple linear regression has k and then k minus 1, or n minus k minus 1 degrees of freedom in the denominator. So let's go to the F distribution chart. We're looking at 5% level. It has 3 degrees of freedom in the numerator because the degrees of freedom for the numerator is k. We have 3 independent variables. So we're looking at this column. And then it's n minus k minus 1. If we go back to our chart, we'll know that we have 7 observations in total. 7 minus 3 minus 1 gives us 3 as well. So this is the intersection. That is our critical value, 9.28. So let's go back to our Excel sheet. Critical value, 9.28. So we are going to reject the null hypotheses because the test statistic, 42.4547, is greater than 9.28. We can also make that the same decision by looking at the p-value. We're going to reject the null hypotheses if the p-value is less than alpha, P-value is 0.0059. Alpha is 0.05. Let's put a 0 up there. Make that a little easier to be read. So we are, again, going to make that same decision using the p-value process. So this basically means that the overall use of the three independent variables, this model is significant. It does have a significant relationship or association with the dependent variable. The next step we can do is we can actually test the three let's call those in the three independent variables to see if those by themselves are significant or not. So the decision rule, this is a t-test process. The decision rule will be to reject the null hypotheses if the test statistic is greater than the critical value. Here is the test statistics right in there. We don't know the critical value. Oops, let's color that in yellow. The critical value is going to be found on our t-distribution chart. We are testing at 5%. This becomes a two-tailed step, and we have n minus k minus 1 degrees of freedom, so we have 3 degrees of freedom at using this column. 0.025, so we have 3.182 as our critical value. So using the t-test process, 9.6167 is greater than 3.112, so we are going to reject it for, I'm going to write this over here, reject. We are going to do not reject for the attic insulation, and we are going to reject once again for the age of furnace, because the age of furnace 4.0356 is greater than 3.182. So that's why we would reject it for the mean outside temperature and the age of furnace, but not for the attic insulation. We can also make this decision using the p-value approach, basically meaning that reject the null hypotheses if the p-value is less than alpha. Alpha is 5%. Here's our p-values. Let's color in those something like that. These values have been adjusted for a two-tailed test. So the p-value for mean outside temperature is 0.024. It is less than alpha, so we reject the null hypotheses. The p-value for attic insulation is 0.2033. It is not less than alpha, so we cannot reject the null hypotheses. That's why we have do not. And 0.0274 is less than alpha, so once again we reject the null hypotheses for the age of the furnace. Now just that ends the process for the hypotheses test for the individual independent variables. Just wanted to highlight here that these test statistics in yellow, these can be computed by taking the coefficient of slope for each of those independent variables divided by the standard error. And there we go, 9.6167. Go back to our PowerPoint here. We've looked at that data. There's the hypothesis test for the overall test for the model. Reject the null hypothesis if the p-value is less than alpha. The null hypothesis is written as this, that all slopes are the same and they equal 0. Should actually have that in there. Equals 0. And that the alternate hypothesis is that they do not equal 0. For the regression test for the independent variables, the null hypothesis is that the slope for each independent variable is 0. Alternately, it's not equal to 0. It's a two-tailed test. There's our test statistic that we looked at, the slope divided by the standard error of the slope. Critical value can be found using those degrees of freedom and our decision rule.